Okay, yeah, so I'm the next speaker, helped by Sebastian. I'm Arno, I'm a statistician focused on experimental design. We will be applying this to SciML in this talk, and Sebastian helped me with some of the trickier programming aspects. And Sebastian is gonna start by introducing some of the background SciML material that you need to know to be able to perform experimental design.
Hello. So, as we've seen in other talks, we have a lot of in the field of scientific machine learning, and as we know, this combines the idea of using our existing mechanistic scientific models with experimentally acquired data, and how we can best combine them to produce better results and to fill in missing gaps. In this particular case, we are looking at some missing parts in a larger known model, and we have examples such as these pictures where we have some reactions where you might not know everything, but you know a lot of the surrounding reactions and the surrounding terms are very well known, but there are some concrete missing parts in the model. And to showcase this better, we're going to start with a concrete case study on a bioreactor. So that's the bioreactor in question, and we already know quite a lot about bioreactors. So what does the system do? So we have three main differential equations, and physically what they represent, we have concentrations of substrate, which is CS, and then we have concentrations of biomass, because it's a bioreactor, so there are some tiny creatures in there that eat the substrate, which is the food, and of course the volume of this entire thing. So we can control the volume by pumping in more substrate, so that's more food for the biomass, so it will grow. So we know that, for example, by pumping in substrate, which is this Q in, we're going to increase the volume. We know that if you increase the concentration of the substrate, then you're going to have more biomass because they feed on that. You know that if you have too much, sorry, so let's go back. Yeah, when you pump more, so the term right there. Sorry, I have the mouse for a reason. So when we pump more substrate, we're going to decrease the concentration, because it's going to get diluted. We know that if we have the biomass, is eating from the substrate, so that means that the more biomass we have, this is going to, again, decrease the concentration of substrate. And we know almost everything about the system, but as we've seen, there are certain parts here that we've symbolized with this neural network symbol. So this is the part that we're going to try to find out. So now, how are we going to do this? This is the moving to the experimental design part. So we want to design a series of experiments such that we can get these terms, and then after that, as we've seen with neural networks, we can interpret their results with symbolic regression. And we're going to use again the symbolic regression.jl package, which will help us understand the output of a neural network in terms of a symbolic expression. And now moving on to the experimental design part, the as I was saying, we are gathering data by pumping that concentration. So we are going to start first an experiment where we have a low substrate concentration. And we're going to see how does the reactor behave in this case. And what we can measure in here are these blue dots. So this is our experimental data that we're going to use in this case. And then after we perform the experiment, we have our model with the neural network inside. We train the neural network. Then after we have this neural network trained, and that's the orange line, then we will perform symbolic regression to understand what does this neural network look like in terms of a symbolic expression, so that we can understand the behavior of the system better. And we're going to repeat this process several times. And as you can see here, we have more candidates for symbolic regression. So these dashed lines are candidate models that were discovered with this process. So first train the neural network, then do symbolic regression during the result. We get several candidates, and each candidate is going to be a dashed line in these plots. And if you're wondering what's the blue line is the correct model. This is what we would expect to get. So this is the correct model. And as we can see, we get pretty good fits with the data. When we actually look at the missing physics component that we're interested in, we see that we are not that close outside of the region of small substrate concentrations, which is where we have gathered data for. And this makes sense. The neural network is not able to extrapolate past the regime where we collected data for and where it was trained. And what happens is that when we look at the possible candidates of component models that are predicted via symbolic regression, we see that we have two groups of two categories of models, essentially. We have a category of models that says, okay, the substrate concentration will, so this mu will continue to increase as the substrate concentration increases. And another category of potential models which says that it's going to remain low with an increase in the substrate rate concentration. So this is the growth rate that we have. And the true growth rate is this one, which is given by monokinetics. And this is what we are trying to see if we can recover by experimental design techniques. And here the important part that I want you to remember from this slide is that we have these two groups of candidate models. One says that this should increase, one says it should remain the same. And now I'm going to pass to Arno.
Okay, thank you, Sebastian. So the experimental design criterion that we used for designing our second experiment is written down here, but I can explain it in very simple terms. So we have these 10 plausible model structures produced by symbolic regression, and they give us different predictions. And then we will be performing the second experiments under those conditions where these predictions are as different as possible from one another, because once we then gather the data, at least some of these predictions will be incorrect. They will be then removed from the top 10 structures of best possible model structures, and they will be replaced by other plausible model structures, and in this way you can come to a sequential experimental design technique. So when we apply this criterion to the second experiment, we see that an experiment where the maximum amount of substrate gets pumped into the reactor. So a lot of food is pumped into the reactor, and then yeah, as Sebastian clearly explained, there were two groups present in the top 10 plausible model structures, and this experiment allows us to discriminate between these two groups. The two groups will give us very different predictions, and then once we perform the experiment, one of these two groups at least is going to be eliminated. We actually performed the second experiment here, and now we see here that because we are pumping a lot of food into the reactor, we see that the substrate concentration grows very quickly, and then once the biomass grows exponentially here, we can see here that at the end, finally the substrate concentration is starting to go down because there is so much biomass present in the reactor that it starts to get eaten. So now when we look at our missing physics panel here, what we see here is that now we have a group of observations at high substrate concentration from our second experiment, and we still have present a group of measurements at low substrate concentration from our first experiment. And we see here that the neural network that we fits well at low concentration and at high concentration, but at, let's say, the middle here, medium concentration range, there is still a large discrepancy between the neural network and the true missing physics. And the same story goes for the 10 best possible model structures that symbolic regression can come up with. All of them fit well at high concentration and at low substrate concentration, but there is substantial uncertainty at the medium concentration range, which is to be expected because we don't have any experimental data in that regime yet, which then leads me to our third experiment. And this figure here is what really convinced me that there was something to this method, because a very clever experimental design was chosen here. I said that there was a lot of uncertainty at the medium concentration range, and what we see here is that first a small amount of substrate gets pumped into the reactor, which causes the substrate concentration to increase to this medium concentration range. Because there is a lot of uncertainty here, a lot of uncertainty in the prediction by the plausible model structures, we see here that the predictions start to diverge from one another. Yeah, then as time goes on, the biomass is eating the substrate, is eating the food, so the amount of biomass increases, and they start eating more and more substrate. So to keep the reactor at the medium concentration range, where there is substantial disagreement between the plausible model structures, we need to keep pumping in more and more substrate into the jar to keep feeding the more biomass that keeps growing in the reactor, which is why this staircase profile is optimal. So what we really see here is that this experiment automatically tries to reduce the amount of uncertainty that was present at this medium concentration range. So this is really a very clever experiment, completely designed or chosen by the computer. After gathering this third data set, we can see here that the true model structure is recovered by symbolic regression. It is kind of in a funny form because symbolic regression doesn't know that minus can be replaced by a plus sign, and it has two divisions here, and it also doesn't know that it can just replace that by a multiplication by Umax. So it is kind of in a funny form, but the true model structure is recovered here. So one step that still requires some human intuition is selecting the final model structure. So it still takes some human input to figure out that these model structures that come before here are underfitting the data, and that the model structures that come after are overfitting the data. So that part is still not completely automated, and there can be still some improvement in that aspect of the algorithm. So that was the optimal experimental design methodology. We did a comparison where we just pumped a random amount of food into into the bioreactor, a random amount of substrate. We gathered a similar amount of data, and then you can see that symbolic regression is not able to find the true model structure at all. So you can clearly see the added value of going for an optimal experimental design strategy. And then, yeah, I will hand it back over to Sebastian to talk about the methodology that we used.
Yeah, so the demo presented here and all of these examples are available in the SciML showcase documentation. So if you go to the latest release of the SciML docs, you can find this, and there's also a QR code for this. And the main things that were used here were, of course, modeling toolkit neural nets, which had a talk earlier, and also the symbolic regression.gl package, which is a very nice ecosystem on its own. And the idea would be to how to best combine all of these technologies across Julia ecosystems to deliver more interesting ways to discover missing physics and do optimal experimental design in the context of universal differential equations. Thank you. I think you'll have a microphone. Yeah.
So, great presentation. Question. Well, more of a comment, and I'm sure you know as well. It really feels like the fitting of the symbolic regression is very misleading, because the task at hand is you already have a data-driven model that fits your curve, and what you're keen on is really finding an expression that makes a statement of not just the training data, but where this thing operates outside of that regime, which matches your dynamics. So, I don't even know. Is there such an interface in symbolic regression that allows the instead of the fitting criteria to just be the training data, to at least help someone looking at the list of equations that you put out there, in the case where you don't know the equations? I mean, in some of these cases, you know, thankfully we knew the actual expression, so we could pick out from the list of what was presented, hey, this is the correct one. But in the case when you don't know that, it seems like the most fitting way of doing such a thing is having some kind of validation on some additional trajectories that weren't part of the system. Are you aware of anything in symbolic regression that actually accounts for that during its a criteria of, I mean, it has the criteria of complexity, but.
So in symbolic regression, you can also use custom loss functions, which you could use to potentially incorporate other things in there. You would have to work with the symbolic regression, like dynamic expression representation there. So there are several approaches here. You can also work at that level. You can try to, as you mentioned, have some data that you are going to use for predictions and evaluate. So not use the entire time spent for training, use a part of it. Or you can also try to get back the expressions from symbolic regression and plug them back into the original model and then see how that goes. So there are several approaches here, and maybe Arno wants to also add some more. So if you have any other comments.
Yeah, just to more broadly answer this question. This is kind of an issue all over experimental data. So when you have observational data, it's very simple to just split up your data set into a test and a trained data set, because, well, if you just select a random subset, then they have the same statistical properties. But when you design an experiment and then you want to later on validate, then yeah, how do you pick what to validate on, because you pick your own experimental conditions. So I think just in general, there is not one way to do this in the literature, not even for very basic experiments like linear regression, and then of course definitely not for these more complicated scenarios like symbolic regression. So it's an issue all over the experimental design literature, in contrast to observational data.
Yeah, thank you so much for an amazing talk. So something I was really curious about is I've used a bit of symbolic regression high energy physics, and something that we have run into is finding a good way to estimate the uncertainty in the choice of function. Not really, in the fitting parameters of that function, but since symbolic regression outputs multiple possible candidate functions for your data, how do you quantify exactly what might be a reasonable uncertainty band for that function? Have you guys thought about that at all?
Yeah, this was kind of what I was alluding to at the end, that it still requires a lot of human intuition to select the final model structure. There really isn't any way to do like some type of more rigorous inference to really get to like a confidence region or confidence set for the possible model structures that we are aware of. We are also not really researchers in symbolic regression. I'm more in experimental design, and Sebastian is more in computer science. So we are also not experts in that area. Maybe you can ask Miles, the creator of the symbolic regression package. He's going to probably be able to answer that better than we can.
So something else that I was a little bit confused by was why in the study we're using both a neural net and symbolic regression. It seems like if you're just looking for something to predict your data, symbolic regression on its own might have been fine, no?
Yeah, we can use this new feature in symbolic regression for that, where they have like these templates now to do this. And indeed, that's the next thing we're planning on doing, on cutting out the neural network. And we have to finish that paper before November.
Yeah, just to comment about that as well. I feel like when you're trying to at least discover the missing physics and whatnot, it's very nice to be able to have a continuously differentiable function that you can just kind of learn your data for first, and then use that conveniently to find your symbolic regression. It's unclear how performant it would be to do the search inside of the actual like causalized causal equations. And I think it's yet to be seen whether or not one would work for the other. So I'm curious, what is your intuition of the performance of doing something like that?
Yeah, I think it is indeed yet to be seen. It does have the advantage that you cut out the noise that is created by your misspecification of your neural network. Like your neural network is never going to fit exactly. So if you cut it out, then that's one aspect that you gain. The downside is, of course, that when you put directly the differential equation into symbolic regression, then you have to solve it again and again. So that computationally it might be more expensive. But I'm also not sure if that's really true, because otherwise you have to put in the neural network into the differential equation solver, which is also very expensive. So that's kind of depending on how much the code is optimized. Yeah.
We'll have to see.
No more questions? Well, I guess I'm going to have to ask to thank myself again then. Sebastian, of course.